This is Jeff McCullough at St. Mary's Episcopal School, and I am doing Chapter 15 on correlation. So scatter plots, association, correlation, they're all related. Scatter plot is what this guy is, where you have an x and y and plot the points. And you really want to look at the scatter plot before you look at the correlation or the association. You want to kind of see it visually first. There are three things you want to look for with your scatter plot. And those three things are direction, and they're basically different types of direction here. So I would say that this one has a positive direction, and that just means that as x increases, this is x, and this is the y-axis. As x increases, y is increasing. As x gets bigger, the y values are getting bigger. So in general, sometimes in psychology you just put an ellipse around this, or sometimes in math we all do a regression line here that kind of fits the data. And so we can definitely see that this is a positive slope, and so it's a positive direction. So this direction is positive. Whereas this direction, as x is getting bigger, the y value actually is going down. As x gets smaller, the y value gets bigger. So this is a negative direction. So you either put an ellipse with there, or the slope of that line that would go through there is a negative slope. This one seems to have a lot of scatter to it. That doesn't seem to be a clear direction. Typically we'd draw a line with a slope near zero and basically say this one doesn't have a direction. It has no pattern, no direction. The form of a scatter plot. So there are two types of forms basically for y'all that you will see in this chapter, which is one is more of a linear pattern where it's going to be a straight line, either as a negative direction there, or curvilinear. Curvilinear, you might see kind of an obvious curve to the data, and it might be exponential, it might be quadratic, but if it's a gentle curve, in stats we tend to make that, we'll re-express the data to make that straight. You don't really do that in psychology. How closely these points lie in respect to simple form a straight line. So this is a positive direction, and how close this is. This looks like a perfect. If I put a line there, a linear line, it perfectly matches the data. And so the R value on this one, which is the strength, would be 1, actually, a positive 1 in this case. This one would be negative, and it would be a negative 1. So the closer you get to 1, the stronger that is. And those are perfect models. They fit the data of a linear line perfectly on both of those. Now these are both strong. These are perfect, literally. Both of these would be perfect. Both of these are pretty strong still. And if I were to fit a line or were to put an ellipse around that, it's you can see the trend of the data. It's definitely linear. It's close to the line. And here it's also strong. And it's not maybe quite as strong, but it's not bad. And so this might be like negative 0.8 or something. This might be 0.85. I'm just taking a guess here. But those look pretty strong. Anytime it's close to 1 or negative 1, it's getting pretty strong. This might be moderately weak or moderately strong. And you see a pattern there. That's a positive pattern. That's a negative pattern. Maybe this might be like 0.5 or something. This might be like negative 0.5. I mean, here it's pretty weak as far as the strength here. There's a lot of, you could still maybe see some direction here, possibly. You can maybe see some direction here, but it's getting weaker and weaker here. So this would be very low, maybe 0.2 or 0.1, and this might be like negative 0.1 or something for the R value there. Correlation, how strong is it between weight? If we had to put a number on this, so again, this is going to be, you can kind of look at the strength of this, how strong is it? It's definitely positive, maybe 0.7 or something like that for your R value. I haven't mentioned this yet, but this has a name. It's called the correlation coefficient. And it tells you both strength and direction. This is the formula for this. Honestly, most students are just going to use technology, either Excel or a calculator or a computer program, to figure out the R value. Very rarely do we ever figure out R values by hand. It's kind of a standardized, we were talking about earlier about z-scores. These are kind of standardized. You can see the x minus mean divided by standard deviation as part of that formula. That might be why R doesn't have any units. It's always between -1 and 1. Measures the strength and the direction. And so here an R value might be 0. Here it's 0.3. You can see it's definitely some kind of positive. Definitely stronger here, maybe 0.9, and this would be perfect. Just give me more examples so you can see that. You get good at estimating. This is kind of a big, important thing. It's true in stats and psychology. Correlation does not equal causation. So sometimes we get a very high R value, like the R value might be 0.99 or, pretty high. And we might be thinking, oh, that's a great fit. Or maybe we might be thinking that the X variable caused the Y value to happen. And that's never true. Scatter plots can never cause we can never use them as a cause. In fact, we have to look for what in stats we call lurking variables. I think in psychology they say just hidden factors that you're looking for. Here's a great example. It's kind of a classic example, actually. If you plot this data, ice cream sales, it tends to be linear data here, and it actually is a very good fit. The R value is very high, 0.9 or higher even. And shark attacks. And so shark attacks tend to go up when ice cream sales go up. Well, that's kind of interesting. So we call this the predicted variable. The Y variable is predicted. The X, predicts the Y variable. So some people might say, well, stop selling ice cream because more sharks are going to attack if you sell ice cream. And that just sounds ridiculous, and which is just kind of an obvious case of misusing a scatter plot. There's probably a lurking variable. There's a hidden variable here that may be causing the actual shark attacks and ice cream sales actually also. And that probably be heat. In the summertime, the ice cream sales are going to increase, and the shark attacks in the summertime are going to increase as well. So that may explain why these have a very high, this is a strong relationship, a strong correlation there, even though ice cream sales are not really predicting shark attacks. We're not really actually causing them, I should say. We're not causing them. We might be able to predict with ice cream sales, but that's because of the lurking variable there. And so you always have to be careful about what's not in your experiment. You have to think about some of those factors. Is there another factor that we didn't account for? We try to randomize with stats, and that accounts for some of the variability. If we do random, we always use some degree of random when we pick our groups and pick our treatments for people. But the other classic example is smoking. For years, they had all kinds of data that basically said, smoking predicted lung cancer, right? And it was a very strong correlation, but they didn't have the data to prove. So for years, even though we kind of knew one might be causing the other, smoking might be causing lung cancer, we couldn't prove it. And so you have to do an experiment. And it has to have a control group. And if you do that, and under the right conditions, everything's been done right, you might be able to prove causation. But to prove cause, you really have to have an experiment with a control group. A scatter plot does not prove cause. In fact, famous mathematician, statistician actually came to the stand in a big smoking trial, and they were trying to get him to say that smoking caused lung cancer, and he said that may be true. And it also may be true that lung cancer is causing smoking. That maybe when you have lung cancer, you have some lesions in your throat, and you might be kind of remedied by smoking. It may make you feel better. And so he actually made the argument that we just don't know, because we need to do some experiments in order to prove that that's true. And they finally did those experiments, and it was proven that smoking did cause lung cancer. But for a long time, we just had some data, and scatter plots cannot prove causation. So that's a real important concept for you. There's another thing called R squared. We call it R squared, but you'll call it coefficient of determination. And it's related to R, but it's a little different. It's a percentage. And it's how good a fit. So if your R squared value was equal to 0.95, that's a very good fit. The closer that percentage is to 1, the better fit your data is in the model that you're putting to that data, whether it be a linear line or a curved line. The R squared value is how good a fit. So the closer to 1 it is, and that will always be a positive value because you're squaring it. So closer to 1, the better the fit. If it's not very much, like if it's R squared, the coefficient of determination was 0.05, well, that's not a very good fit to your data. You might want to look for a different model or something. In stats, I don't think you have to know this, but we describe R squared, or the coefficient of determination, as the percentage of variation in Y that is explained by X. And so here our R squared value very high. Our ice cream sales, let's see, so in terms of this, let's say we had a 95% correlation, we would say something like the percent of variation in lung cancer is explained by in shark attacks is explained by ice cream sales, and you could talk about it that way. This other thing I want to mention was the truncated range. It decreases the strength of the correlation coefficient. Remember, the correlation coefficient is called R. It's decreasing the strength. You can see if you look at the original data, that is fairly strong, moderately strong, or strong might be the data there. But if you only look, if you kind of, in a sense, block out this part and block out this part and only look at this data in between here, well, now I don't know what the pattern is. I can't tell that it has a positive slope, a positive relationship. It's not clear from the data there. Or even if I truncated it this way and took a small sampling here, it'd be hard to see exactly what the pattern is just looking from that little piece of data there. So when you truncate, it loses some of that power because the range in either range in X, or the range in Y has been shortened, and that is going to cause your graph not to be as accurate there. I want to mention one more thing dealing with z-scores that we mentioned in Chapter 14. So let's say you have a z-score of negative 2.3. So if you looked at kind of a basic normal curve here, in the middle, z-score-wise would be 0. 1 standard deviation out, we would have 68% of the data in there, and that's plus 1 standard deviation and minus 1 standard deviation to get to this point. A z-score of 2.3 is positive, so I'm going to go 2 standard deviations plus a little bit. So maybe like right here would be a z-score of 2.3. In other words, each standard deviation this measures z-score. So if I wanted to do, say, a z-score of z equals negative 1.5, then I would go 1.5 standard deviations out to the left in a negative direction, and that would be z equals negative 1.5. I just wasn't sure if that was clear from the last video. I kind of ran out of time, and I want to make sure you knew that z-scores, you can kind of draw them on a normal curve, and so anytime you're over 2 or 3 standard deviations out, there's very little area out there. So if I were to draw the area of that, it's very little area. Remember, the area of everything under the curve adds up to be 1. So essentially, the area of this is the probability of getting a z-score of 2.3 or bigger. Whatever area that is, it's going to be a very small percentage, essentially, of 1. And so area really works to be a percentage there. And so sometimes we're figuring out the area underneath a curve. It's really a calculus concept in a way. In fact, you can use integral to figure that out, which is a calculus method. It's one way of doing that. And we also have stat methods called norm CDF. Like in a calculator, we can do a norm CDF command and that will actually figure out the, on a normal curve, from something to something, like in this case, you might say from 2.3 to infinity, figure out what the chance is of that happening.